Okay, welcome to the lab here. So what I've decided is since our lab today, which is experiment 13, is on empirical formulas and there's some post-lab on molecular formulas, since I think we only got a few more examples of where we left off there in terms of empirical formulas, molecular formulas. We're just going to finish up talking about the last of these and just do a few more examples to make sure everybody's on the correct page here. And again, that will help with the experiment, which is 13 today, about empirical formulas. So we're going to finish the rest of these up. And like I said, then we'll talk about the experiment towards the end here. So we were finishing in lecture talking about how to actually calculate the empirical formula. And again, just a reminder that to calculate the empirical formula, you basically need to convert things into grams. So again, very commonly they are given to you in that percent composition of by mass. So you need to convert that into grams, and you could do that easily by assuming again 100%. That basically means that you'll have the same percentage as grams. They'll be the same numbers. Makes it easier. Again, as we just did there at the end, we want to convert into grams into moles using the molar mass, divide by the smallest number of moles, and that hopefully should give you your empirical formula. So since we just did one together, why don't you try this one, which should be the next one on your sheet there, and then we will talk about it. So here we're looking for the empirical formula of this guy. And again, if you need some info here, carbon 12.01, hydrogen 1.008, and our friend oxygen there still 16. All right, take a few minutes and calculate that. Here, I let people in. Again, if you're just coming in, we're going to continue lecturing since we're almost done with this chapter here, and it's about empirical molecular formulas, which is what the lab's about. So we're working on this example right here. So give it a go, and then we'll talk about it in just a sec. Okay, let's take a look here. So in this case, we have three different elements happening. We have the percentages of each. Always a good idea to kind of take a look at the percentages and make sure you add them up, and they really should come to about 100%. They may not come exactly 100%, maybe a little bit over, maybe a little bit under, but they should be in the 100% area. And if we add up all those percentages, they do come to 100%. If by some chance you do that and it doesn't come to 100%, that does mean you're missing something like an element or something like that. There should be some way to figure that out in that type of problem. So in this case, it does come to 100%. So we're going to assume 100 grams. And again, the purpose of that is it just keeps all the numbers the same. So that basically means we have 49.3 grams of carbon in this case. We also have 6.9 grams of hydrogen. And if we assume the 100 grams, 43.8 grams of oxygen. So really the next thing that we want to do is take all those grams and convert them to moles. So we're going to use the molar mass from the periodic table to do that. So 1201 for our carbon, 1.008 for our hydrogen, again from the periodic tables where we're getting these numbers, and 16 for our oxygen here. And if we do all that good stuff there, it looks like we will end up with 49.3 divided by 12.01 gives us like 4.105 moles of carbon, 6.845 moles of hydrogen, and 2.738 moles of oxygen. So all we're just simply doing there again is converting from grams to moles. And we do that so that now we can divide everybody by the number of moles, the smallest number of moles. So in this case, the smallest number of moles does look like oxygen. So we're going to divide everybody by oxygen's number. So when we divide, obviously, oxygen by itself, we get 1. When we divide the carbon by oxygen's number, we get about 1.5. And when we divide hydrogen by that number, we can type it in, right? I'll try that again. 8 or 5 divided by 2, 7, 3, 8. We get 2.5. So at this point, our empirical formula would be C 1.5, H 2.5, and O. Problem with this is, as we talked about, that's not so good because they all need to be whole numbers. So this would not be the correct empirical formula. So to clear it, in this case, we actually need to clear both of them, but they both end in 0.5. So we need a factor to multiply everybody by to get whole numbers. And actually 2 looks like that factor there. So if we multiply everybody by 2, we would end up with C3H5O2 would be our empirical formula. And again, that's basically 1.5 times 1 is 1.5, 1.5 times 2 is 3, and also 2.5 times 2 also works to get us a whole number. So that factor of 2 is what we want to multiply here to get us our whole number, and this would be our correct empirical formula. Question on any part of that there?
How did you get 2.738?
I took 43.8 and divided it by 16, and you should get 2.738. And 16 is the molar mass of oxygen, so that's why we divided it by the 16. Other questions on that?
So if, let's say that you had like two different values, like let's say that the carbon and hydrogen like weren't both like the 0.5 ending, like, and you had to multiply to get different numbers to find the empirical formula, like would you just pick one to choose, like go with, or would there never be a situation like that?
There really shouldn't be a situation like that, because basically the empirical formula is the simplest whole number ratio of the molecular formula. So by that being said, when you take it from, say, molecular formula to empirical formula, you would be dividing by the same sort of common number, which means that you should be able to find one number that would fix everybody's problem, and that, like we just did here. So you really probably wouldn't run into a situation where, you know, you would need to like multiply one guy by 2 and one guy by 4 or something like that. Again, because they're all basically related to each other by that simplest sort of whole number relationship, that ratio, you should always be able to find like one number that should fix everybody else. Other questions? Also, just a point here as we're looking at this stuff, obviously we're dividing all these things by moles, and that's what we could kind of think about these guys here as. These are really the moles of each of those guys as well. So that's an important sort of relationship, as we'll see a little bit later on when we talk about certain types of calculations. All right, let's try another one here just to make sure. So you have this one next. So we're looking for the empirical formula here of aluminum and oxygen, and aluminum is 2698 and oxygen is 16. Okay, so let's take a look at this one. In this case, we're not actually given any sort of percentages. We're just given the grams. So don't go backwards. Don't figure out percentages or anything like that. So we're just going to kind of continue forward here, which basically means we just need to convert our guys from grams to moles. So we got our 4.151 grams of aluminum. We'll use our molar mass from the periodic table of aluminum, which is 2698 grams per mole. We also want to convert our oxygen into moles using the molar mass, which is 16 grams per mole. So if we do that there, we get, looks like 0.15385. Take it a couple of digits, moles of aluminum, and 3.692 divided by 16 looks like 0.23075 moles of oxygen. So here again, we're going to divide by the smallest number of moles. And in this case, it does look like oxygen. No, it looks like aluminum is our smallest. So 0.15385. That's going to give us 1. We're going to divide this guy by 0.15385. And in that case, it is going to get us not 1. It's going to give us 1.5. So again, here we didn't hit a whole number. So we have aluminum, oxygen 1.5. So we need to clear that. So as we saw last time, a factor of 2 should clear that. So that would give us Al2O3, which is aluminum oxide. And by the way, all ionic compounds are empirical formulas. So that's why when we put together an ionic compound, simplest way to get to 0, they're always empirical formulas. And that would be the correct one in that particular case, Al2O3. Any questions on that particular one or how to calculate empirical formulas? Okay. So in addition to calculating empirical formulas, we're sometimes asked to calculate molecular formulas as well. And there really is sort of 3 things that you need to calculate the molecular formula. And really those 3 things that you need to calculate that molecular formula is you really need first the empirical formula. So that may require you to calculate the empirical formula like we've been doing, or it may be given to you. So again, if the empirical formula is not given to you, you need to calculate it like we've been doing. Once you've calculated the empirical formula, the second thing that you really need is the molar mass of the empirical formula. So you need that empirical formula. You need to calculate the molar mass of the empirical formula. And the third thing that you need is the molar mass of the compound. The good news about number 3 is that is usually given to you in a problem. So usually in a problem, they will say something like the molar mass of this compound is 180 grams per moles, or the molar mass is, they may even give you a range, like the molar mass ranges from like 90 to 110 grams per mole. But somewhere in the problem, they will give you the actual molar mass of the compound. So really it comes down to whether or not you sort of need to figure out the empirical formula like we've been doing, or if they give it to you, you obviously don't need to do that calculation. So what you do with those numbers is you take the molar mass of the compound, which again is usually that number that is given to you, and you divide it by the empirical formula molar mass, and it will give you a number. And that number is what you multiply the empirical formula by, as you can see here. So for example, let's say we divided that and that number we got was 4. And let's say we had an empirical formula of C2H4. We would multiply everybody there by 4 and get C8H16. And this would be our molecular formula in that particular case. Or you could write it by putting parentheses and the 4 on the bottom. Like I said, I think earlier, most people will kind of distribute it in and write it like this, but you could technically put parentheses and sort of the number on the bottom there. So those are really the 3 important things empirical formula, molar mass of the empirical formula. And again, when you divide those two, you should get a whole number. This one for sure, if you're not near a whole number, you could round. Usually it should be pretty close to a whole number when you do that division part. And if it's not, even if it's really not so close to the whole number, usually in the case of this, it's okay to round. Not so much in the empirical formula calculation, but in this calculation, it's usually okay to sort of round to the nearest whole number. Questions on that there?
I had a quick question. For when they give you the molar mass, do we need to do anything with that when we're finding the empirical formula, or is that only for the molecular formula?
So usually it's only for the molecular formula, so you really wouldn't necessarily need to use it for figuring out the empirical formula. You would just use it really for this calculation here that's on the screen, where you would take that molar mass that's given to you and then divide it by the molar mass of the empirical formula. So usually that's strictly for more the molecular formula that molar mass is given to you.
Okay, thank you.
You're welcome. Other questions? So why don't we try one? So this is the one that we did earlier where we figured out the empirical formula. So at this point, why don't you figure out what the molecular formula here would be? So it's the same sort of empirical formula example we did earlier, and that was the empirical formula from earlier. And a reminder, carbon 12.01 and hydrogen 1.008. All right, take a minute or two and figure out what the molecular formula would be. Okay, so on this particular one, again, if we didn't do the first part earlier, you would have to go through all the steps to figure out the empirical formula like we did previously. But now that we do have the empirical formula given to us, the other thing that we do need to get is the molar mass of that empirical formula. So that is 3 carbons at 12.01 plus 7 hydrogens at 1.008. And that would get us something like 4309, we'll call it. So now that we have the molar mass of the empirical formula, as mentioned before, in these problems, you will be given the actual molar mass of the compound, which is 86.2. To find the molecular formula, we're going to divide those two numbers. So 86.2, we're going to divide it by 4309. Again, should give us the factor to multiply the empirical formula by. And in this particular case, that factor is a 2, which means we will take our empirical formula and multiply it by 2. That gives us C6H14. or you will sometimes see people put the empirical formula in parentheses and a little number on the bottom. I would say most people, again, would go with this approach here. Question on that there? All right, let's see what we got going here. There it is. All right, it agrees with me. That's good. Let's actually, let's see. This is the other. So we did that one. Let's do a new one here and just mix it up so we're not looking at the same one. Let's do. Let's say we had a compound that was 43.64% phosphorus and 36% oxygen. And has a molar mass of, let's go with 283.89. What is the empirical formula and molecular formula? I'm going to try a fresh one here all the way through. All right, so molecular formula, empirical formula for something that's 43.64% phosphorus, 56.36% oxygen, and has a molar mass of 283.89 grams per mole. Phosphorus from the periodic table is 3097. And oxygen is still 16. All right, give that one a go, see what you come up with. Okay, so let's take a look at this one. So again, we want the empirical formula and molecular formula. So in this case, we do need to kind of go through the empirical formula process first. Again, we have a couple of percentages. It does add up to about 100%. So we're not missing anything. We again could assume that we have 100 grams. That's going to keep our numbers the same. So we're going to take 43.64 grams of phosphorus. We want to also convert that into moles. So we'll use our molar mass of 3097 to do that. That also means that we would have 56.36 grams of oxygen. Again, also using the molar mass for oxygen from the periodic table to convert us into moles. And if we do that, looks like we get something like 1.4091 moles of phosphorus and 56.36 divided by 16, 3.5225 moles of oxygen. Just like before here, we're going to divide by the smallest, which in this case is phosphorus. So we're going to divide everybody by that 1.4 number. That's going to give us 1 for phosphorus. And for our other one there, 2.5 looks like it. Again, at this point, this is not good for our empirical formula as we do not have all whole numbers. So we've seen our 2.5 a lot here today. So we're going to multiply this by that common number of 2. That will clear our 2.5 and also give us whole numbers for everybody. So the empirical formula here would be P2O5. Any questions up to that point? So remember that when you do want to solve for the molecular formula, you need 3 things. You need the empirical formula, which we just got. We also need to figure out the molar mass of the empirical formula. So that would be 2 times our 3097 for our phosphorus, plus our 5 times our 16 for our oxygen. That is going to give us a molar mass of our empirical formula of about 141.9. And that's the second thing that we need to find the molecular formula. And the third one, which is the molar mass of the compound, which is usually given to us, is the third thing that we need. So we're going to take the molar mass that was given to us. We're going to divide it by the empirical formula's molar mass. And that should again give us a factor to multiply our empirical formula by. Happens to be 2 in this case. So we're going to multiply our empirical formula by 2, giving us P4O10, looks like a winner. And that would be our molecular formula. Any questions on any of those steps or how to calculate a molecular formula, empirical formula, any of those things? Okay, so this is probably the right approach and the right way to sort of do these type of problems. But while we're talking about a problem like this, I'm going to show you an alternative approach that sometimes people like a little bit better or to do it this way. And this works really mainly for when you have to find the molecular formula, maybe the empirical formula as well. But you do need a couple pieces of information to sort of approach it in this way that I'm going to show you. You need the molar mass of the compound given to you, and you do need to know the percentages of each of the elements that are present. And we basically can take sort of a percent composition approach here. So for example, if we take that information there that we had, which was the molar mass of the compound there was 200, what we got there, 283.89 grams. And we know that the percentage was 43.64 phosphorus and 5636% oxygen. So this approach here actually works from the molecular formula to the empirical formula. So basically, this is the mass of the compound, and this mass is based off of all the elements that are present. And we know that out of this mass, 43% of it is phosphorus. So we actually can convert our percentage into a decimal by dividing by 100, gives us 0.4364. And we could times it by the 283.89 grams. And what that will give us is about 123.9 grams. That's phosphorus. At this point, we could use the molar mass from the periodic table for phosphorus, which is 30.97 grams per mole, and convert those grams into moles, and we would end up with 4 moles. We could do the same thing for our oxygen, which would be 0.5636% oxygen. Again, the whole thing's molar mass. And what that would give us is 0.5636 times 283.89 gives us about 160 grams of that is oxygen. We then could use the molar mass of oxygen. And if we do that, we end up with 10 moles. So what we just calculated is the molecular formula, P4O10. So this is a way that you could actually go right to the molecular formula if you know the mass of the compound and the percentages of each of the elements. And at this point, we know that this is 4 phosphorus to 10 oxygens. We could divide everybody by 2 there, and that would be the same as 2 phosphorus to 5 oxygens, which means our empirical formula would be P2O5. So this is an alternative approach that sometimes people will do when they have that information given to them. They have the mass of the compound, the percentages. You could actually go to the molecular formula and then just reduce it down to the simplest whole numbers to get to the empirical formula. And the nice thing about that is that sometimes people like it because, you know, you don't have to worry about, you know, I got 2.5, I got to find that factor to maybe multiply by. So again, this is an alternative approach. Can only be done with a molecular formula sort of problem when you're given that information. Obviously, if you're not given the molar mass of the compound, you can't actually do this approach. Questions on sort of that approach? Okay. And as you can see, we do end up with the same formula as we got going the other way. All right, and one last thing to sort of tie everything we were talking about together here in this chapter is let's just take that formula there that we got, the P4O10, and let's say we want to know how many atoms of oxygen are there in 12 grams of P4O10. So kind of tying everything together here, our molecular formula, empirical formulas, moles, Avogadro's number. If we were given a problem like this, a couple of things we should think about, like we talked about, this is atoms, which means we do need to use Avogadro's number. We also have grams, which means we do need to use molar mass. But there's a difference here. We're looking for just the oxygen. We're not looking for the entire thing. So we do need a way to go from the entire formula to just the oxygen part. And you can use the actual formula as a conversion factor. So when we say P4H10, as I mentioned before, and as you can see in those calculations we were doing, these are actually the number of, these are the number of moles. So you could actually come up with like a mole to mole relationship using the formula. We could say that in every 1 mole of the entire thing, there is 4 moles of phosphorus, like we just calculated, and the 4 comes from here. We could also say that in 1 mole of the entire thing, there is 10 moles of just the oxygen. So we could actually use the formula and the idea that these little numbers on the bottom are moles to actually come up with sort of a conversion factor to go from the whole thing to just say the oxygen part, or we could go to just the phosphorus part. So if we were going to do that, because this is a mole to mole relationship, we do need to convert the grams into moles. So we would take our 12 grams of the whole thing, and we would want to use the, oh, I can't put O with this guy. I want to put H for some reason. So P4O10, we want to use the molar mass of this whole thing. So I'm just going to steal the number we used before, 283.89. And again, that is the molar mass from the periodic table of this whole thing, 283.89 grams per mole of the whole thing. That's going to cancel out the grams of the whole thing. And if we got a number, again, you don't necessarily have to get a number at this point, but if you got a number, you would end up with something like 0.04227 moles of the entire thing. Again, here we are not interested in the entire thing. We're interested in just the oxygen part. But now that I have it in moles, I could use that relationship from the formula to do that conversion, to go from the whole thing to just the oxygen part. And if I do that, 0.04227 moles P4O10, again, using the formula as our conversion factor, 1 mole of the whole thing gives us 10 moles of oxygen in this particular case. And that would get us times 10, 0.4227 moles of oxygen. So by using the formula as a conversion factor, I was able to go from the whole thing to just the oxygen, which is what I'm interested in this question. And now what I have is moles of oxygen, but I need to get to atoms. So this is where we could use Avogadro's number. And if we do that, 0.4227 moles of oxygen, like we did earlier, Avogadro's number here is going to go on top, 6.022 times 10 to the 23 atoms per mole of oxygen. And that will end up getting us, we'll go with 2.5 times 10 to the 23 moles of oxygen. So that is a very sort of common thing that is sometimes asked. You're sometimes asked, especially when you're doing, say, moles and atoms and things like that, of just the one element and not the whole thing that's in the formula. So as we can see here by doing the empirical formula, molecular formula, again, those little subscripts are moles, and you could actually use the formula as sort of a conversion factor. Question on that? And if we wanted to do something with just phosphorus, it would look the same, except that at this point here, obviously we would use phosphorus relationship, the 1-to-4 relationship. Any questions on anything we talked about in this chapter? Moles, molecules, atoms, any of that stuff there?
Would the answer for this one be atoms, or would it be more?
It would be atoms. Thank you very much.
Gotcha. Okay.
I wrote the wrong one. Thank you. You see, I want to be done too. No, I'm just kidding. Let's see. So these are atoms here. Thank you. It would be atoms of oxygen. Perfect. Again, the moles here would cancel and we would be left with atoms. Thank you. Other questions on that? Okay. So that is chapter 8. So let's talk about a couple of things here. Let's see. Let's talk about when everything is due. So a reminder that I did move exam 2. So exam 2, which will include chapter 8, which we have now just finished. will be on 10/26. So I believe that should be not this Monday, but a week from Monday. Again, activity 10 and 11 was due today. Yes. So make sure, hopefully you got those up. That should be your nomenclature stuff. Pre-lab for 12, 13, and the lab report for 12 and 13 will be due this Friday. Yes. So 10/16 at that point. Any questions on any of that stuff there? So let's just talk about the experiment here and what you need to do from the experiment. Let me punch it up here. Okay. So I just want to talk about the actual physical part of the experiment, and then I'll tell you what you will need to do from it. So let me do that. So in experiment 13, we were going to be looking for the empirical formula of a magnesium oxide, I believe, of magnesium oxide. So in this experiment, what was going to happen is they were going to take a crucible. And again, that crucible is what we used in that last experiment, 12. And obviously they're going to weigh it empty. They obviously would put in some magnesium into that. And well, they would put the magnesium in there. And obviously from the difference of that, you would get the mass of the magnesium to start with. They would then take the magnesium that's in there, and they basically would heat it up. And as they heat it up, there's oxygen in the air that will come in and combine. And they would heat it up. They would cool it down, kind of like what they did in the hydrate. They would reweigh. They would put it back up there again and heat it again with the magnesium, some oxygen in there at this point. And again, cool it down and reweigh. And they would continue that process until they hit constant mass. So the idea here is when they hit constant mass, they have pretty much put on all the oxygen that there would be. Oxygen in this case is like the excess reagent. There's plenty of oxygen in the air. Magnesium is like the limiting reagent. It's going to eventually be all used up at some point. And when they're all done, they hit that constant mass. They should have a crucible at the end that has magnesium and oxygen in it. And that would be at the end of the experiment. So what we need to know in order to figure out the empirical formula is we need to know the grams of magnesium, and we basically need to know the grams of oxygen. The grams of magnesium is easy, is the mass that you started with. Now, when we subtract what happened at the end from the beginning, if we just sort of think about what's in those crucibles at the beginning of the experiment, just magnesium. At the end of the experiment, we had magnesium and oxygen in there at the end. So if we subtract these two things, that will give us the mass of the oxygen that was there. And at that point, you would have the grams of oxygen. Like I said before, you would have your grams of magnesium. And at this point, you would do an empirical formula calculation. You would convert your grams of oxygen into moles. You convert your grams of magnesium into moles. You divide by the smallest, and you get your empirical formula at that point, just like we've been doing in sort of these examples in class here. Question on sort of the process that was going on in this experiment. All right, so the good news is we're not going to watch the video. Yes. All right, so the better news maybe is the only thing that you need to do for this lab is just the post-lab questions. So for experiment 13, You just need to complete the Postlab questions. So it's going to ask you to calculate some empirical formulas. It's going to ask you to calculate, I think, some empirical formulas and some molecular formulas. So that'll be some good practice. The reason I just explained to you what was going on in the experiment is a couple of those Postlab questions are basically kind of similar to what goes on in this experiment. So, for example, you have, say, in the first Postlab question, it talks about cobalt reacting with chlorine to give you a cobalt chloride. So sort of the same idea as what we were just talking about, like in your crucible to begin with, you had cobalt. At the end of the experiment, you had the cobalt plus the chlorine. And basically, again, if you subtract those two, that is how you get to the grams of chlorine, the grams of cobalt at the beginning. And at that point, you convert it into moles, divide by the smallest, and you can figure out your empirical formula. So a couple of those questions on the Postlab are sort of related to sort of the procedure. And again, that's why we just went over the procedure. So hopefully that will help you sort of visualize what's sort of happening in there. Question on that. So experiment 13, the only thing that you need to do is just I think there's 4 Postlab questions, if I'm not mistaken. So 4 Postlab questions about empirical and molecular formulas. That's all you need to do and turn in by Friday. So you should be able to hopefully do that, I would hope. We're not going to do we're not going to watch the video for it. We're not going to do the calculations for the experiment itself. So just the Postlab questions for 13. 12 is the whole experiment like we did, right? So we did the whole experiment on 12, which is the hydrate. 13, just the Postlab. Again, when you upload it, that's really all I need, just the Postlab questions. So you don't have to upload the entire report or anything like that. So just the Postlab question. And again, the pre-labs for both of those guys, along with the lab reports, will be due on Friday. The latest, you could turn it in before then, but the latest, it will be due on Friday. And that also includes the pre-lab questions online, and also the written sort of pre-lab as well. So make sure those guys get in there as well. Let me take a quick look at one last thing, and then I'll be quiet, I think, we'll call it a day here. So schedule-wise, where we're at, just so we're clear what's going on next week before we call it here. So we are at the 12th, 14th, so next week, okay. So next week, on Monday, we will lecture, obviously. So we'll be rolling into chapter 6, I think, and then probably 7, which is chemical reactions and types of reactions. Again, on the schedule there, obviously the exam has been moved. So we're going to be doing some lecturing on Monday and obviously lecturing on Wednesday, and we will pick back up in terms of experiments on Wednesday with experiment 14, which again, the pre-lab will be due on Wednesday of next week, like normal. So as we talked about last time, everything will be kind of due like it normally is. And like I said, the the exam will be moved to the 26th. And I'm thinking what's going to happen is we will move experiment 15 to the 28th. And we'll just push flame tests off somewhere along the way. We either will do it or not do it. So that's sort of the game plan. So Monday is going to be some lecturing so we can get caught up again on some of these topics. Wednesday, lecturing in experiment 14. Monday, a little bit of lecturing, then exam during lab on the 26th. And then on the 28th, experiment 15. Any questions on any of that there? Okay. Other than that, thank you for listening. Sorry about the torture here today. But make sure you get all that stuff in. If you have questions, I'll be more than happy to answer them. If you're good, I'm good for today. Have a nice weekend. But if you do have a question, I'll be happy to answer. Make sure you turn in all that kind of stuff. Make sure you put here if you haven't done so. And if you're leaving, have a nice